Singapore, please.
Good morning, ladies and gentlemen. I'm Kanchon from Singapore, and today I'll be presenting on problem number 5, Leidenfrost stars. The problem statement tells us to place a water drop on a hot surface, and under certain circumstances, it develops oscillating star shapes. We're to induce different oscillatory modes and investigate them. The relevant parameters includes the mode number of oscillation, the size, surface tension, and density of the drop, and the substrate temperature. Here's our content for today. Firstly, we'll look at our experimental setup and video analysis procedure. Next, we will discuss our theoretical model for the natural frequency of a water drop. Furthermore, we will examine the driving mechanism and self-excitation of the droplet and look at some further insights on the mode transition. Now, I will move on to our experiments. Our experimental setup consists of an aluminium hot plate illuminated by a halogen lamp. We used a mirror and high-speed camera to capture footage of motion of our droplet as shown in the mirror view. We used cartridge heaters to heat up our hot plate and a thermocouple to record its temperature. These are connected to our thermostat, which allows us to accurately determine the temperature of our substrate. In addition, we measured the temperature at various points of our hot plate using a thermocouple. We observed a maximum temperature difference of 0.8%, which shows that our temperature distribution is indeed uniform. In our video analysis, we first performed a background subtraction on our raw video to better visualize our droplet contour. We then binarized our video to obtain our process snapshot and used computational edge detection to accurately extract our experimental droplet profile. We then performed a two-dimensional discrete Fourier transform on our experimental droplet profile. We observed a bright band corresponding to our DFT peak, which allows us to accurately determine both our mode number and frequency of oscillation. In our preliminary observations, we can observe the normal modes of oscillation of our drop, as we can see over here. For larger drop sizes, we tend to observe higher modes of oscillation, as seen. When the drop size is increased even further, we can observe even higher modes of oscillation. Additionally, we also observe drops that exhibit the superposition of normal modes. Shown here is a drop oscillating at the third and fifth mode simultaneously. From our 2D discrete Fourier transform, we observe two bright bands corresponding to each mode. Moving on to our theoretical model, we will first discuss our two-dimensional model, where we will treat our drop as a cylindrical column. We can write down our droplet contour profile as a Fourier series as follows, where A0 denotes the mean radius of our droplet. Applying volume conservation, we can obtain this expression for the mean radius, where A is the static droplet radius. We can then obtain the potential energy of our droplet by integrating across its surface, where sigma denotes the surface tension of our fluid. For small oscillations, we can write down the velocity potential as follows for potential flow and implement the following kinematic boundary condition. Integrating the velocity potential, we are able to obtain our kinetic energy, where ρ denotes the density of our fluid. Now that we have obtained both the potential and kinetic energy of our droplet, we can substitute them into the Euler-Lagrange equation, which allows us to arrive at the following expression for the oscillation frequency. However, we know that surface tension and density are highly dependent on temperature. Hence, we measured the droplet surface temperature using a thermal camera, which allows us to accurately determine the value of surface tension and also density. Plotting our experimental oscillation frequency against drop size, we observe a consistent deviation from our 2D analytic model. And hence, we'll move on to a more rigorous 3-dimensional model to account for the finite height of our droplet. We begin by writing down the shallow water equations as follows, which takes the projection of our droplet onto the horizontal plane. We can then integrate our pressure across the height of the droplet to obtain a term due to gravity and a second term due to surface tension and the curvature of our droplet. We then impose appropriate boundary conditions for our droplet. We begin by applying the volume conservation, which allows us to define our modified boundary. Then, we can equate the pressure at the boundary, taking into account the curvature of our modified boundary. Finally, we can write down the following kinematic boundary condition to relate the velocities at the boundaries. Linearizing our system, we obtain the following expression for the oscillation frequency, where we see that h0 denotes the static droplet height. However, we note that the static droplet height must be determined using a sessile drop model. We will begin our sessile drop model by writing down the hydrostatic Young-Laplace equation. Writing down appropriate constraints and boundary conditions and applying the conservation of volume, we can solve for our static drop height numerically using the non-wetting condition. Plotting our experimental oscillation frequency against drop size, we can see that our 3D model is able to accurately predict the oscillation frequency. As we increase our drop size, there is a decreased curvature at the edges of our droplet. This decreases the restoring force due to surface tension, resulting in a lower oscillation frequency. Additionally, we can plot our experimental oscillation frequency against varying modes. And we can observe a good agreement between our theory and our experiments. As the mode number increases, the curvature at the sides of the droplet increases. This results in a greater restoring force due to surface tension, and this will hence increase the oscillation frequency. However, we note that there is a limited experimental range, and this is due to our driving mechanism, which we will be explaining later. Lastly, we also carried out experiments using acetone, which has a lower value of surface tension. Our theory predicts a decreased frequency due to a decreased restoring force, and we can see a good agreement in our experiments. Now, we will look at how the oscillation begins. To investigate this, we connected a pressure transducer to the bottom of our hot plate using an airtight tube. We then connected the pressure transducer to a digital oscilloscope, which allows us to accurately determine our vapor pressure. We observe fluctuations in the vapor pressure over time. We can carry out a fast Fourier transform to convert this signal from the time to the frequency domain, and this allows us to accurately determine our pressure frequency from our FFT peak. Plotting our pressure frequency against droplet frequency, we observe a trend where the pressure fluctuates at twice the natural frequency of our droplet. Furthermore, we also observe the formation of capillary waves before the onset of the droplet oscillation, and this can be seen clearly from our side view. To understand how the capillary waves are formed, we note that the rapid evaporation of the droplet will create a region of high vapor pressure below the droplet. The resultant outgassing of the vapor layer will produce a large shear stress on the bottom of the droplet, and this leads to an unstable growth of capillary waves due to interface instability. This leads to the self-excitation of the droplet, as the propagation of capillary waves causes periodic fluctuations in the drop radius and serves as the source of the periodic pressure fluctuations. We hypothesize that this is a parametric excitation mechanism where the driving frequency is twice the natural frequency of the droplet. Modeling the droplet as a damped parametric oscillator, we can write down the damped material equation, which consists of a viscous damping term and a parametric driving term, as the drop radius is modulated in time. We note that omega b denotes the natural frequency, which we recall is given by the following expression. We see that the energy input from the driving allows for a sustained oscillation in the presence of viscous dissipative forces. Solving the damped material equation, we can plot the driving amplitude epsilon against the driving angular frequency. We observe an initial rate region where there is an insufficient driving for resonance. Next, stable decay regions can be observed in blue, and this happens when there is no oscillation. Lastly, unstable growth regions are observed in purple, which corresponds to the resonance tongues where oscillation occurs. We see that the most unstable solution occurs when the driving frequency is twice the natural frequency of our droplet. Experimentally, we observed that the frequency of the capillary waves just before the droplet oscillation is indeed twice the frequency of the star-shaped oscillations of the droplet. Hence, we can conclude that parametric resonance is indeed the driving mechanism for the droplet oscillation. Now, we are ready to look at some further insights on the mode transition process. We begin by plotting sample mode transition trajectories across 15 experimental runs. When the drop is first introduced, we observe mixed modes of oscillation. However, this quickly decays to a well-defined n equals to 7 oscillation, followed by a transition to n equals to 6 and n equals to 4. Afterwards, the drop continues to decay until it becomes a sessile drop where no oscillation is observed. In our experimental runs, we observe that specific modes tend to be preferred at specific drop sizes. Furthermore, due to the complex transient behavior of our droplet, it is highly challenging to reproduce our mode transition pathways reliably in our experiments. Additionally, we observe that droplets tend to oscillate within a certain range of frequencies. Since the driving frequency is dependent on the vapor flow rate, we will expect the driving frequency to lie within a preferred range. Taking a closer look at this range, we observe that specific modes are possible for a particular drop size. Hence, as drop size decreases due to evaporation, lower modes will be excited due to parametric resonance. Now we'll look at the mode transition process. Before the transition, the drop exhibits a well-defined n equals to 5 oscillation. Next, we can observe a superposition of modes n equals to 5 and 3 during the oscillation, as can be seen from our discrete Fourier transform. Finally, the drop exhibits a well-defined n equals to 3 oscillation, as shown. In conclusion, we have come up with both a 2D analytic model for a cylindrical column and a 3D numerical model to account for finite height. We also carry out extensive experimental verification of frequency. We also studied the driving mechanism for our droplet and the formation of capillary waves and modeled the parametric excitation of our droplet. Lastly, we also examined the mode selection mechanism qualitatively and experimentally investigate the mode transition. Here are my references, and thank you.
Questions from the opponent, please.
So, thank you for your presentation. I liked it very much. My first question would be that what defines the frequency of these oscillations?
The frequency of the oscillation would be the frequency at which the star-shaped patterns of the droplet repeat themselves over the oscillation.
Yes, but what physical parameter defines this frequency?
So
what is the most relevant parameter?
So there are several key parameters in the frequency.
What would you say is the most relevant? The most biggest effect on this?
The biggest effect, I believe, it will be the surface tension and the mode number.
Okay. And did you try to change surface tension by putting some soap in the liquid? If that's the most relevant parameter?
I believe when we tried...
A short answer, please. Did you or didn't?
I tried to vary the fluid using acetone, which has a lower surface tension, and observed a lower frequency.
Oh, thanks. How did you measure pressure difference beside this drop?
Beside the drop, as in under below the drop, we used a pressure transducer, which we connected to an airtight tube through a small hole at the bottom of a hot plate, as can be seen over here, and we then connected.
Thanks. And do you have any theoretical predictions for the maximal modes of the oscillations?
We know that since our driving frequency...
please a short answer.
So
yes or no?
Yes.
Yes, and what is this number?
Maximum modes for a given drop size we can predict. However, there is no...
Yes, but you said that the frequency depends on the drop size. What's the maximum mode you can achieve?
Theoretically, we have an infinite.
Short answer, please.
Infinite.
Sorry?
There is no limit to the...
No limit, okay. So, and you could produce this measurement too?
We could not observe this in our experiments due to the...
What was the biggest number you could achieve?
The biggest number we could see was 12.
12. Okay, thank you for your answer.
Thank you very much.
Questions from Team Hungary, and I will oppose your report. So, at first about the overview of the report, I like your report very much, and I think it was clear and it discussed mentioned almost all relevant points of this problem. So your theory was based on energy and surface tension, so you said that surface tension is the most important parameter that defines the frequency, with which I agree. but your experiments were well planned, so you could you used a hot plate and you could control its temperature very good, and you had a very high camera with a very high speed camera. Your comparison of your theory and your measurements, I liked it, so I saw a good number of graphs, and the fit was also very good. And my overall impression was that the theory was described to a sufficient detail. However, the basics of it, I feel that was not. I missed some few points in the basic understanding of the phenomenon, which I will discuss in the discussion. Then you didn't really say anything about the understanding the errors of the measurements or their reproducibility, while, as I said, the basics were not discussed really properly. So, about the problem statement, I should have expected that you say a few words from the case when the droplet is not oscillating, it's just on the plate, and why it happens, and you should have induced this phenomenon, and I didn't really see that you put a droplet on the plate, it was not oscillating, but after that you induced the phenomenon, so I missed that. But I think that you define the conditions for this phenomenon pretty good. So about the evaluation of the theory, I think it was a really good, clear physical explanation. So it was a detailed theory, you use more methods, and the main message was properly emphasized, so it was really clear. While also it had some weaknesses. So, as I said, I missed the basic explanation of the phenomenon, why these exactly these shapes appear. Then you said that he said something about the volume conservation, which I don't think it's pretty appropriate, because the volume of the air is decreasing in time. While you didn't really talk about the airflow, or I missed a few parameters there. Then about the measurement. I think that you showed the setup of your measurements very well, and you used a camera with a sufficiently high frame rate, while most of the most relevant parameters were investigated experimentally. However, I missed one parameter, the change of the surface tension. Then you need an appropriate number of measurements, but you had a convincing agreement to your theory. Then about the weaknesses, as I said, the effect of the different voters were not investigated properly, in my opinion, while there were unclear sources of measurement errors. So on the whole, I found that the explanation for the phenomenon was not sufficient, in my opinion. So that I will want to discuss. I like your theory very much, and your experiments too. And I think that you compare your theory with your measurements to a sufficient detail. And I would like to call you to the discussion. So,
thank you very much, and please start discussion.
Thank you for your presentation again, I like it very much. And my first question would be that, do you think, would this phenomenon be observed when there are no hot plates, but a simple air flow, so you flow air from for example, a hovercraft or something like that? And
yes, I believe this is indeed possible to be observed, because from literature we know that the droplet excitations...
Could you use the mic, any mic, please?
Yes, I believe this is indeed possible to be observed. In literature, we know that it is possible to observe these star-shaped oscillations where we use a pulsating airflow below the droplet. So we are supplying airflow over here, and this keeps the vapor layer from being stable. And because there is a stable vapor layer and the outgassing of the vapor layer, there is a radial flow, and this radial flow will cause a large shear stress on the bottom, and this will excite capillary waves, which allows for parametric driving of the oscillation of the droplet.
So you say that in the case of a simple constant airflow, the phenomenon should be observed?
Yes, indeed, it's observed in literature. We know that the required conditions for the oscillation of the droplet would be a stable air layer below the droplet, and also for our case, the substrate temperature will have to be above the Leiden point for a stable air layer.
And what you're saying is the driving mechanism of the case when there is no temperature change. So in this other case which I mentioned, so there is viscosity of the water, which is a damped oscillations. You model this phenomenon as a damped oscillation, but you also have an excitement. What is the excitement in this case?
The excitement would be due to the radial flow of the vapor layer. In this case, we use a pulsating airflow, as we have discussed. This will cause a large radial flow, and this radial flow will cause shearing at the bottom of the droplet. So this shear stress will cause an instability at the fluid interface, which is well known in literature and documented in a paper from the 1950s. And this will cause the formation of capillary waves.
Okay.
These capillary waves travel up the droplet and
Thank you very much. I would like to ask the explanation. You said that the frequency is the most relevant parameter. Surface tension is the most relevant parameter that defines this frequency.
Yes, and this is because if we consider equilibrium drop, the surface energy is minimum,
yes.
And this is a
yes. So there is an equilibrium state, or
there is a circular equilibrium state.
Could you observe this stable equilibrium state when there was no oscillations?
Yes, when the drop is simply a sessile droplet, it will be in stable equilibrium shape, and in the plane view, the contour of the droplet will be circular. However, when we have an external driving or a perturbation, the drop can exhibit different shapes and undulations in the edges of the drop. So for this case, we'll see that if we analyze a small fluid element at the boundary of the drop, the surface tension will provide a restoring force
yes.
for this oscillation, and this is what restores the oscillation.
And don't you think that mainly the only thing that will influence the frequency is the surface tension? Because if we make the model of a pendulum, for example, which is an oscillation, then this frequency of the oscillations will be defined by the mass on the, for example, on the spring and the spring constant. And in this case, I think that these two effects can be modeled by only the surface tension.
No, I do not agree. You need to
can you show me your results at different shapes, so different modes? So I think that the frequencies were almost the same.
No, they are not.
They can be considered constant, so around this value.
No, I do not believe the frequency can be considered constant for different modes. This is because when we have an increase in the mode number, say this will be mode 2, now we have a mode 4 oscillation.
Yes.
The curvature of the drop would be greater, and we know that when the curvature is greater, there is a greater restoring force from
yes.
the surface tension. So the curvature of the drop will also increase the surface tension, increasing the mode number will increase the restoring force. This increases the frequency.
Do you think that these oscillations can be approximated with a sine wave?
Yes, because we see
yes.
that.
Thank you. I was only interested in that. So, and could you please go to your first slide? Because there I couldn't see the circle. Because if it would be really a sine wave, then we could see a circle. Then the do you see what I mean? So there would be a phase like this. We have phase like this, then these amplitudes will be reduced, and I think that if they were a sine waves, then we could see an exact circle at some point, and I couldn't observe that in case of your measurements, and I think that you can't approximate this as sine wave. It's because the amplitudes of these oscillations are very big, and therefore it will be an harmonic. And I think that's the reason, but as you know, the frequency of the oscillations, in case of unharmonic case, the frequency of the oscillations will be defined by the amplitude, or it will be changed. And I think that's why you could observe changed amplitudes, changed frequencies, because the unharmonicity changed.
No, I do not agree, because in our experiments, we see that the reason why we cannot observe a circular shape is not because the amplitude oscillations are not a sine wave. This is because of the nonlinear effects of the droplet oscillation. We see that when our amplitude is slightly larger, this will cause excitation of the secondary mode, and this is because of a complex mode coupling between the primary mode, for this case will be n equals to 4 and n equals to 8. Therefore, at the equilibrium point, what we will be seeing would be a superposition of the primary excitation and the secondary excitation. So we understand that the nonlinear, what I mean by nonlinear superposition is that the waves will not simply add up, and for mode coupling this occurs when the dispersion relation breaks up, applicable to small amplitude waves. So from our results, we can expand our potential energy to third order, and if we solve for time evolution of each of the foreign components of our droplet, we can observe some secondary harmonic excitations, and this accounts for the fact that why we cannot see a perfect circle. However, we can observe something that is very, very close to a circular shape, as the secondary excitation is normally one order of magnitude lower than the primary excitation.
I think that it's really close, but I can't really understand why can it be considered a sine wave. There is no circle. But let's move to another point. I think, did you observe oscillations in the vertical dimension?
I do not observe any significant vertical oscillation. What you might be seeing because of what you might be perceiving to be the vertical oscillation could be due to the capillary waves traveling up the droplet. So as the capillary waves travel up the droplet, they will move towards the top of the drop and towards the center, and this can cause some apparent movement of the top of the drop. So for this case, from our side view, we see that the height of the drop will perhaps be around 3 mm for this size of the droplet. You can see that the vertical oscillation is extremely small and the amplitude is extremely negligible. Furthermore, this is also not our driving mechanism.
Thank you, that was convincing. And now I will have one last question to your theory. You said that volume is conserved during the process, is that right?
By volume conservation, I meant that during one oscillation of the droplet, which occurs very fast, normally on the time scale of 0.05 seconds approximately, we will see that there will be negligible evaporation during this period. So when we are solving for the steady state oscillation, yes, volume conserved.
So to summarize a little bit for the theoretical part, I think that the approximation of a sine wave can't be used in this case, as we could have seen on the video on the first slide, that in case of a sine wave, a circle should have been seen. So, and I think I should go to your measurement part. What was the biggest, so you said that the biggest number of modes you could achieve was 12 modes.
Yes, and we observed.
What was the reason for that?
We know that this is due to setup limitations because we have hot plate has a limited size, so we are not able to introduce even larger drops onto the hot plate. We know that for larger drops, you exhibit higher modes of oscillation, but due to experimental limitations, we cannot do this. Furthermore, if we were to use a larger hot plate, it would be very difficult to heat the hot plate evenly, and the temperature distribution might not
be done. Do you think so? If the droplet has a certain surface tension, then after a time, in my opinion, the air will come up in the center of this droplet, and therefore this whole phenomenon shouldn't be observed.
So by the air coming up, do you refer to the chimney effect? The air bubble rising through the center of the drop?
Sorry?
Do you refer to the chimney effect where the air bubble rises through the center of the drop due to vapor pressure? So we see that sometimes we can indeed this chimney instability, and this is more common at high temperature. However, we see that an explanation for this would be because of the large amplitude.
But it would be even larger. Then I think I can't really imagine that there is no limitation for the modes. So at a given surface tension, there must be a limitation when these bubbles come.
No, I still do not agree, because we know that the bubbles only rise when the vapor pressure fluctuations have a very large amplitude. However, if we were to use a lower substrate temperature, these vapor fluctuations would not be of a would not be a very large amplitude, and the bubbles do not tend to be observed when we use a very low temperature.
Okay, thank you very much.
Okay, thank you very much for the discussion.
Could we switch to my...
Can we start the time and get the opponents?
Could we switch to my last?
Can we get opponents' presentation on the screen, please, technicians? Thank you.
Okay. So thank you very much for the discussion. I think that we discussed some interesting points. At first about the basics physics. So we were talking about the basic explanation of the phenomenon. And I was not fully convinced about this explanation, because I think that the basics of this motion is due to the surface tension of this droplet, which we agreed. But so in my opinion, only that influences the frequency and the unharmonicity. So, and then we talked about the theory. I said that the oscillations were not harmonic, which he wrongly assumed, and therefore his theory had some problems in the basics of it. But he said that he couldn't change the surface tension of the water, which is a very interesting effect, but because he should have he could have seen some interesting points, and we also talked about his measurements. And finally, I would like to thank for the discussion and thank you all for coming and seeing us.
Thank you. Questions from the reviewer, please.
Today I will show you, I want to ask some questions firstly. What's the difference between Leidenfrost point between acetone and the water?
Could you repeat your question?
What's the minimal temperature when Leidenfrost effect appears to the acetone and the water?
Oh, this would depend on the surface of the substrate because we know that this would depend
But what
on
was the value of this difference?
For aluminium hot plate, it's 275 degrees Celsius.
But
The temperature difference.
Okay.
Difference is 175.
What's the temperature of the plate constant?
No, we vary the temperature of our plate to investigate its effects on the pressure and also the oscillation.
Now questions to the opponent. You have said here that the supertension is the mechanism which put the water together, but which mechanism put out water to continue oscillations?
Well, it's the air below this droplet, and I think that as the droplet begins oscillating, so we have to induce the phenomenon. And
Thank you. Have you observed the relation between the temperature and the number of moles?
We know that at higher temperatures, the evaporation rate of the droplet is also higher.
But with higher moles, you observed higher number of moles.
No, this is not true. At higher temperatures, we cannot observe the higher moles, and this is because it is hard to observe a pure mole at higher temperatures due to the rapid transition between the moles due to the evaporation.
Okay, thank you. And now, what's the mechanism which put the energy through the surface to the drop? Is it convection, radiation, or conduction?
I believe the two most significant ways of heat transfer will be conduction and radiation, since after
According to this, what was the temperature difference between the bottom of the drop and the top?
the bottom of the drop would be around 90 to 100 degrees Celsius, and the top plate would be around 300 to 400 degrees Celsius, so you can do the math, around 200 degrees Celsius.
Okay. What was the humidity around in your experiments?
We do not believe this will significantly...
No, I thought it was big or small or in the middle.
It should be minimal because it was conducted in an aircon room.
Okay. What was the capillary length of the water?
Capillary length of the water would be around 2.7 millimeters.
And according to this, what was the shapes of your stars?
The
Shape of your stars.
shape of
The drops before they start to oscillate.
The shape of the stars before it oscillates would be circular, as I said, its equilibrium point where the surface energy is minimum due to surface tension.
In your problem, you assumed that we have flow in the drop in the 3D, and how was the boundary condition on the bottom of the drop when they evaporate?
Could you repeat your question?
I'm sorry that the time for questions is over. I'm sorry for that. Thank you very much.
Welcome, ladies and gentlemen. My name is Lewandowski, I represent in Poland. Today I will show you our review to task number 5, Leidenfrost stars. The main point of this task was to put the drop on the hot surface and observe Leidenfrost effect. And Leidenfrost effect is one of the conditions when the stars appears. So it had to be investigated in this task. And the conditions when this phenomenon appears was explained during presentations because of evaporation of the drop. But in this evaporation changed with different humidity and the circumstances of the plate under the drop. So it wasn't investigated statistically. Second part of this task was to investigate the circumstances when this drop appears. And in this presentation, we observed, we could see the explanation why it appears, but no investigation what are the circumstances when this drop appears. Circumstances, I mean the conditions of the surrounding another drop, as a temperature, parameters of the evaporation of the liquid, as a heat transfer, as a heat conductivity, And it was done partially because we have a very nice model and investigation of the frequencies of oscillations of the stars. And the third part of this task is to, according to the measured before the circumstances when the drop appears, to construct own methods to induce the stars with control number, mode, and amplitude. And it was done partially because it was investigation about when theoretical investigation when the stars appears, but no construction own method with to control the conditions around the stars. This presentation has had the positive aspects as an analysis of the flow in the drop, compared with measurements the theoretical model with analysis of the flow in the vertical part, and explanation why the stars start to appear because of capillary length. But also in this presentation haven't included anything about the conditions when the stars appears to control, to investigate when this capillary length appears and what's the source of instability to capillary waves. We had to also in this task explain what are the conditions for different oscillatory modes, and in this presentation included this dependency on the radius of the drop, and we observed a decreased tendency, but it isn't only one parameter of the drop and the surface we could change in this task. It also depends the most of the energy transfer between the surface and the drop, and this frequency and this number of modes and the frequency will depend on these conditions, and it wasn't explained during the presentation completely. Secondly, in this theoretical model, assumed, as I heard during the presentation, that we have cylindrical drop, and I believe that the drop also could be spherical, and this flow inside the drop will be completely different, and it will be when the capillary length will be smaller than the radius will be smaller than capillary length. Secondly, we heard during the discussion about the vertical oscillations of the drop, which appears when the number of modes is 1, and as said the reporter, it doesn't appear, but it's well-known effect in the literature. Then when it starts appears in the vertical oscillations, and it was investigated in the theoretical model because it predicts frequency 0. During discussion, we haven't heard anything about discussion about the circumstances when the star's drop appears, what I explained before, and any investigation about it was a discussion about the shape of oscillation. It wasn't signed, but I really don't see the point why it will not be signed, because during presentation we observed the Fourier transform of the shape of the star, and we have only one peak. It is disconnected with this assumption. To summarize discussion,
I'm sorry. Your time is over.
Thank you.
Thank you very much. 2 minutes.
Thank you for the interesting discussion. So here are some concerns that were raised during the discussion. Firstly, the first concern was on the intuitive qualitative explanation of the phenomenon. However, I provided this by explaining the driving mechanism as the outgassing of the vapor layer below the drop, which produces capillary waves, and also the surface tension, which restores the oscillation. Next, I also explained there was also another concern of the non-linearity of the oscillation. However, I said we see that this only occurs for large oscillation amplitudes and also at higher temperatures. Another concern was raised on the vertical displacement of the droplet. However, we see that this is not significantly observed in our experiments and is perceived only due to the propagation of the capillary waves up the droplet. And furthermore, this does not affect the driving mechanism. There was also another concern raised on the chilling instability of our droplet, and we know that this occurs when the amplitude of the vapor pressure fluctuation is large at larger temperatures, but does not affect the driving mechanism and frequency of oscillation. Lastly, there are some misunderstandings on the sources of error. We obtain our sources of error for the frequency from the FFT resolution and the changes in drop size over the sample duration. So for the novelty of the report, we conducted a systematic experimental verification of the oscillation frequency, varying the mode number, drop size, and also the fluid used. We also experimentally verified the parametric excitation mechanism and also came up with a numerical simulation for the oscillation frequency. So in conclusion, we have come up with both a 2D analytic model and a 3D numerical model to account for finite height and carry out an extensive investigation on the frequency. Next, we also studied the driving mechanism of our droplet and the formation of capillary waves. We also modeled the parametric excitation of a droplet and studied the vapor pressure fluctuations experimentally. Lastly, we have examined the mode selection mechanism qualitatively and experimentally investigated the mode transition process. Here are my references, and thank you.
Thank you. So, questions from the jury members, please. Yeah.
Okay, to the reporter, please. On your slide 32, you talk about fluctuations in pressure, and I was wondering if you are talking about this slow, regular oscillations or this high-frequency noise.
I'm talking about the slow regular oscillations. The high frequency noise is due to the inherent noise in our pressure transducer and from the surroundings.
Okay, and as for the slide 23 in your presentation, what is UR?
Slide 23 is the radial component of the flow velocity of the droplet at a particular point.
Okay, so this is velocity.
This is the flow velocity.
Thank you.
Okay, thank you very much. Tomasz?
Thanks. Could the amplitude, this is a question for all the teams, could the amplitude of the oscillations be controlled and how?
I think that's not a clarifying question for 3 teams.
Sorry.
So can you have something more focused?
These are the properties of the base, and I somehow missed the properties of the amplitude. So if this would be commented by the presenting team.
Maybe the reporter only. Is it fine? Okay, thank you.
At higher temperatures, what we can perhaps observe would be a larger radial flow rate of the vapor layer due to a larger rate of evaporation at the bottom of the drop. So this will produce a greater shear on the bottom of the drop and result in increased rates of energy transfer from the shearing in the vapor layer and transfer energy to the bottom of the drop. And this will result in a greater amplitude of the capillary waves that are excited. When we have a greater driving amplitude, this will also result in greater amplitude of oscillations of our star-shaped oscillations.
Okay, thank you very much. Can we pass it further to? Oh, sorry.
Okay, you said that the source of the parametric force that acts upon the droplet is the fluctuation of pressure. Am I correct?
Could you clarify your question again? Repeat.
You said that the source of the force is fluctuation of pressure, vapor pressure underneath the droplet.
Yes, there's a fluctuation in pressure underneath the
My
droplet.
question is that how come the random air movement turns into periodic?
Oh, this is because of the formation of capillary waves. Because as capillary waves propagate along the droplet, this will actually cause the pressure to fluctuate due to a modulation in the film height, the vapor layer height of the droplet, below the droplet, and this will cause a fluctuation in the pressure in the vapor layer. So we know that this will couple the vapor layer to the capillary waves that are a result of the instability, yes.
Okay, thank you. Elia?
Yeah, you mentioned the Matthew terms. Quickly, can you tell me what information about the physics of the phenomenon is?
We know for parametric oscillators, it's well known that it's most unstable when the driving frequency is twice the natural frequency. At twice the natural frequency, the driving imparts the most amount of energy into the oscillator, and for this case it will be our droplet, and this will cause it to develop oscillations. However, at large driving amplitudes, it is also possible to observe some resonance at the natural frequency, as at the natural frequency there will also be a large rate of energy transfer.
Okay, thank you very much. John, you had a question?
Yes, on slide 28. Looking at the n=2 curve, it doesn't seem to fit with your experimental theory. Can you account for that?
This is because of the over-prediction for very small drop sizes. In our theory, we have treated our droplet as a cylindrical column for the 2D theory, and in the 3D theory, it is treated as a cylindrical column with a semicircular cross-section at the periphery of the droplet. So we know that where lower drop sizes, the drop would tend to assume a more spherical shape, as the surface tension effects would be more dominant than the gravitational effects. So because of this, the shape of the droplet would be more spherical rather than cylindrical, and this is a limitation of our theory. But however, it is known from literature as a similar
Thank you very much.
Okay, thank you. I have a very similar question. If you could come to the slide 29. So just to be sure, so there is no fitting in this theoretical line, or is there any fitting?
No, our theory does not use any
Okay,
fitting.
so then can you somehow comment on the fact that, like, on average the points are very well fitting the line, but clearly the trend of the points is pretty much different than trend on the theory line. So how is it possible that the actual value fits perfectly for the middle points, but the trend is different?
We believe this would perhaps be due to the fact that for the smaller drop centers, this would perhaps be due to the fact that the drop shape is more spherical. And however, for the larger amplitudes, this would perhaps be due to some errors in our solution to a Young-Laplace equation to calculate for the height correction factor.
Okay, thank you very much. I will a little bit break the rule and let you ask Laveria's question if you have one.
Yeah, I'd just like to ask the reviewer, you talked about humidity having an effect, so I just wanted to quickly find out what you sort of thought.
In the presentation, we heard about explanation of the source of this of oscillations of star, and it was because of the evaporation. And evaporation clearly depends on the humidity, and to control humidity, we could control the induced modes and this evaporation. So I think it was really important to control this parameter in the setup.
Okay, thank you very much. We ran out of time, so thanks for that. Converging. Okay, we're ready now. So, could we have the grades for the report? No. It's a 9. 9. 9. 10. 9. Give the end of the chain as well. Opponent, now. 7, 6, 8, 6, 6, 7, 8, 6, 8, 4, and a 7. And the grades for the review now. It's a 5, 5, 7, 5, 7, 7, 8, 6, 8, 6, and a 7. Thank you very much. So it was pretty consistent for the report. But still we had a single 8 by Nero, so it's very unusual to explain the 8 as a single slowest grade, but you would have to do it now. Sorry for that.
My only comments on the recording team is that I couldn't see from your presentation that which part is a repeat of others' experiment, each part is your own contribution. And some other thing is that you could have gone further by trying to study the shape, the whole volume of the water instead of the mode itself. That would have been better.
Okay, maybe can we have the
I gave 3.5 for the whole report, and because of that, I didn't know which one you make your own. And for the discussion, I also gave 3.5 plus 1 equals 8.
Okay, thank you very much. For the opponent, Tomasz was pretty much lower than the rest of the jury.
Okay, so my partial grades are 1, 1, and 1, and okay, just calibrating myself with respect to other teams, I think that you stressed things which are not so much like arguing for too long whether this is a sign or not sign. I think this is a reasonable approximation, and you would go, if you want really to point something out, you had a question how many modes there could be in principle, and if in principle infinity, then you have an opportunity just to ask about say the continuity of matter and stuff like that. But of course other things would be there. It was between 4 and 5.
Okay. Okay, thank you very much. And yeah, to praise a little bit, there were a couple of 8s. So who would like to comment? Ilya? Yeah.
Okay, so in this stage the report was obviously very good, so I think that my colleagues in the jury and me obviously were comparing and weighting the opposition with respect to the report, but at the same time I was also weighting my grade for the opposition against other oppositions I saw in this competition. And in my evaluation scale I want to have quite some differentiation between weaker oppositions and stronger oppositions. And in this context, I felt that your opposition was quite good. It was certainly very well above the average level. My partial grades are 2 for the questions, 3 for the opposition itself, and 2 for your discussion. You were bringing in relevant physics, you were challenging the reporter's understanding, you were challenging the reporter's result, you were challenging the reporter's theory. And again, on my scale, comparing with various other possible oppositions, I felt that the grade of 8 was deserved and adequate.
Okay, thank you very much. And now we have, yeah, we could comment a little bit because the grade was not that small for the grades for the review. So on the lower side, there were people with 5s, myself, Anna, Matthias, and Elia. Matthias or Elia, would you like maybe Matthias?
You was not as thorough, especially from a point of view of the report of the opposition. In fact, in that area, I give 1.36. Some of the points raised by the opponent were not time-wise. That's why.
Okay. Okay, thank you very much. And then on the upper side, Phil, 8. Reviewer.
I thought the review was reasonably well balanced. I scored it as 2.5, 2.5, 2, which came in at 8, and quite balanced.
Okay, thank you very much. So it seems we have done our job according to the rules, and now I think, yeah, everyone is still eager to know the results. I think you think you know the results, but you don't know everything. So, yeah, just to spare some time before they finish and check everything, a few organizational remarks. Very good news, there will be lunch for everybody. Just to make it clear, we didn't really match with the time, so the cafeteria you used to go, or the whatever canteen everyone used to go is closed now. But they are packed lunches for everyone. But they are the packed lunches for us, and they are the packed lunches for you. So packed lunches for the teams on the stage, and the jurors, which were holding their grades today, are up behind this room, and for everyone else, it's down behind this room, as far as I understood. But roughly this information. So, but they are packed lunches for everyone. The second very important thing is we start at 3:30 the award ceremony with we really started. So be sure to be seated here before 3:30 because we start on time. And are we ready now? Yeah, we are ready now. So can I get the envelope with the results? You have to trust me. Okay, oh yeah, we are very ecological. This is an unused score sheet. And on the back side of the score sheet is from the position 4, Hungary, 38.5. Position 3, Poland, 39.4. Very tight, less than a point. Position 2, China, 43 points. And as every time, the winner is Singapore 51.0. So thanks for everyone for coming. Thanks for the jury for judging us. Thanks for the team for the performance. Enjoy your packed lunch outside and be back in time, please. Thank you very much.